Well, we've been discussing the derivative now for several lectures. Remember, the derivative was first introduced in the context of a car moving down a road to find out the instantaneous speed of the car. But later we saw that the derivative also told us things, if we drew a graph, it told us the slope of the tangent line to that curve. And we saw that we could actually take derivatives in mechanical sort of ways so that as a practical matter we can find out these answers. Last time we saw an application of the derivative to baseball, and this time we're going to be talking about how the derivative can be used to make ourselves living in the best of all possible worlds. We're talking about maximizing things and minimizing things. We can apply this technique to maximizing the profit that a company makes, and in fact we will see such a problem and deal with one in lecture number 22. We can use this technique to apply to such things as health issues. In lecture 23 we'll take sort of a humorous example of maximizing our length of life depending on how much exercise we do. But today we're going to introduce the philosophy of how to maximize a situation by looking at a particular problem. And the problem that we're going to be dealing with at first is the problem that I'm sure many of you face frequently. And that is, suppose that you need to build a rectangular field that is enclosed by 600 feet of fence next to a river in order to enclose a field where your camels can roam. Now, this is a very practical problem, okay. But it illustrates a technique, and so it's really actually a great example of the technique. So bear with me on the camels. So here's the idea. Here we have our fencing, 600 feet of fence. And here is the edge of the river, and our goal is to build a rectangular enclosure. Now, when we think about this problem, the first question that comes to mind is, well, what are the different possible shapes for this rectangular enclosure? Well, we could make it very thin and long. See, sort of like a camel run. They could run back and forth, but they couldn't go very far. So it could be very thin, and if you make it extremely thin, then it wouldn't have much area. And then, or you could take some sort of intermediate size like this, intermediate size, or you could make it very tall and thin like this. You could make just a little bit on the river and have a very tall enclosure. So the question is, what shape should you put the fence to enclose the biggest possible area? This is a prototypical kind of max-min problem that is the bane of the lives of all college students in calculus. I hate these things, but I love them, you see, and you're the one, I'm the one you're stuck with, so you should enjoy it too. So here, let's look at some examples here of how we would approach this problem. So we see all of the different possible shapes that have the same 600 feet of fencing next to the river. And when we start to approach the problem, the first thing that we might consider doing, in fact, it seems like the natural thing to do, is to pick some shape that seems like a likely candidate for being the biggest and figure out how many square feet there are for that choice of enclosure. And it seems like a natural shape to choose a square as a shape for the field. And so we could say, just hypothesize that we made our fence into a square shape. That is, we used 200 feet of fence in each of the three sides that are not against the river. And we would see that we would have a 200 by 200 foot field which encloses 40,000 square feet of area. Well, that's fine. And we can say to ourselves, well, that's something, but do we know whether or not that is the maximum area that can be enclosed? What's our strategy here is what we're thinking about. Well, in this course, the philosophy that we've taken to the world is, instead of looking at things statically, instead of just saying, okay, it has 40,000 square feet, now what? Instead, we think dynamically. we think not just that we fix our field at 200 by 200, but that we're varying our choices. And we think about, well, what happens if we make an adjustment? In particular, suppose that we tried, as an experiment, to make the fence a little bit taller and a little bit less long this way. We will always refer to the distance from the river out into the field as the width, even when it becomes longer than the other dimension. In other words, suppose it were 201 feet coming out from the river, and then 198 feet across the river and 201 feet back down. What would be the area? Well, the area here would be, we multiplied it out, 39,798 square feet. Well, in a way, that's sort of confirmatory to our thinking that a square might be the biggest. Because when we made an adjustment in that way, we got a smaller area. Well, let's try adjusting it the other way. Suppose we make it 199 feet up away from the river. That makes it 202 feet across and 199 feet down. We multiply that out, 199 by 202, and we get 40,198 square feet. In other words, we see that the square is not the biggest field that we can enclose next to the river. And we see this not, we see it by actually looking at numbers, of course, but the philosophy of what we're thinking about is if we have a choice, if we want to investigate a particular possible area, if we make an adjustment, we make a change, we can see whether we are increasing the area by making that change or decreasing the area by making that change. Well, that's where the derivative comes in. The derivative is measuring the rate at which one quantity changes relative to another. So now let's think very carefully about this. As we're thinking about all these different possible shapes, what will be the characteristic of the shape at which the area is maximum? That is, what will be the characteristic with respect to this dynamic view of change? Will it be that when we change, the area will increase? No. If we change it a little bit, it's not going to increase whether we increase the width or we increase the length. Any change cannot make a bigger area, otherwise it wouldn't be the maximum. So we're looking for a place where a little bit of change does not have a trend in any direction. In the case of 200 by 200, we see it does have a trend. If we make it wider along the river, we actually increase our area. So what we need to do is systematically look at all possibilities, not just selecting a few because there are infinitely many, you see. So that's not going to work. We need to look at all possibilities. And the way to look at all possibilities is we say, well, once we have chosen the width for the fence, all is determined. Because if we have this 600 feet of fence, once we've chosen this width, well, we've got the rest of the fence left over. The only way we can make a rectangular enclosure is by completing the picture. And we know how much fence is left, and so we know how we know we're going to use W feet on this side, we're going to use W feet on this side, and the rest of the fence will be the length, which is this total, which is 600 feet, minus 2W, which are the two parts of the fence that come out. Well, now we are going to realize that once we've made a decision about that width, we also know how much area is enclosed, because we know what the length is and what the width is. The area is just the product. So we can see that once we've made a choice of W as the width of the fence, the area is the 600 minus 2w times w, which is 600w minus 2w squared. Well, this then is, as you see, a function. It's a function that associates for every choice among all these hypothetical experiments that we could do, all the possible ways to build this fence. It's telling us what the area would be for each individual choice. And now we have our concept. Remember, the concept is that we're looking for a place where an adjustment in the width, the adjustment in the choice, will not either increase nor decrease the area of the fence. If it increased it, well, then we should pick a bigger W. If it decreased it, we should pick a smaller W. You see? So we're looking for that special place where there's no trend. In other words, where the derivative is 0, where it's not increasing nor decreasing for changes of choice of W. So let's just see here. We can actually graph this function. So let's just understand what this means. This says, this is recording what would happen if we hypothetically built all possible shapes of fence. Because it starts with saying that we choose width equal to 0, meaning that we just lay the fence right along the edge of the river. And it doesn't have any width. Well, it has no area. And that is what this is saying, having this be a 0 at 0. Likewise, suppose we made it the width 300 feet. Well, what does that mean? That means that we took our fencing and we just laid it right next to itself straight up in a line. Well, there's no area there either. It's only in the intermediate sizes of choices of W where we get area. And we can see by looking at this graph, A of W equals 600W minus 2W squared, we see that we have this nice curve that represents for every choice of W, we go up here to see what the area is. Now, it's obvious from looking at the picture. Once we've drawn that picture, it's completely obvious where the maximal choice of W is. It's at the place where the derivative is 0. It's at the top place because it's showing what areas you have as possibilities. It's at the top. At the top, the tangent line is horizontal. But remember what the derivative tells us. The derivative tells us the slope of the tangent line, the steepness of the tangent line. Well, the steepness of a horizontal line is 0. So now we have something to look for. We're looking for a place where the tangent line has slope 0. But we know how to find the slope of a tangent line of a function. We take the derivative, and the derivative of 600W minus 2W squared is 600 minus 4W. And then we say, under what circumstances is that derivative equal to 0? Well, 600 minus 4W equals 0. When will that happen? It will be an equation when 600 equals 4W, and that'll happen when W equals 150 feet. So the answer is 150 feet. That's how wide we should make the river and the fence, 150 feet. And here is the picture then of the enclosure when it's 150 feet wide. Now, I want you to notice something about our method. The actual method of finding this maximum value actually it didn't include finding the area of any enclosure. We actually did that. Remember when we tested out the square? We found the area. If it were a square enclosure, we said 200 by 200 is 40,000 square feet. But the actual strategy that we used to find the maximum didn't actually involve finding the area at all at any point. Because all it involved was to find the derivative in order to locate a width where there was no upward nor downward trend as we considered different widths. In other words, where the derivative was 0. So the actual technique never involved finding out what the area actually was. Now, here I'm doing that. I'm multiplying it out for you just to show you that it does have a particular area and that the area is bigger than, for example, the square area was. But that's just for, that's sort of an added bonus. It's not really integral to the part of, to the technique of finding that maximal area. Let's check out that it's maximum by seeing that if we vary the width by a little bit in either direction, we go down in area. We enclose less area. And sure enough, you can see, here's this picture where we make it a little bit taller. We make it 151 tall, which leaves only 298 for the width. And we see that when we multiply those two numbers, we get a number 44,998 square feet, which is slightly smaller than the area enclosed by our maximum 150 by 300. And likewise, if we make the other adjustment, making it slightly wider, sure enough, we have that that product is once again slightly smaller than the 45,000. And that's, of course, what we expect at the maximum. You adjust either way, and you get worse. So this is a wonderful example of how you find maximum and minimum values if you are talking about some varying quantity. If we have an arbitrary graph that is representing the relationship of one varying quantity to another varying quantity, whether it's, for example, what the price of a good is on one axis and what the demand is on another axis, that you can see that you will get a graph, and if you're seeking places where that you have found a maximum value, you don't have to look at all the values to see where that's likely to happen. All you need to do is find those places where the derivative is 0. And you can see if you have this rather complicated graph, well, there are only 1, 2, 3, 4 places where the derivative is 0. Once you find those places where the trend is neither up nor down, you can just individually check them and see, well, which one is the biggest. You've reduced an infinite problem of checking all possible widths of area to just finding a very few. In the case of the camel example, we actually only had 1, but in an example like this, you might have 4 or 5 that you check. So I also, by the way, included in this picture the fact that it might be that there's an endpoint possibility where the maximum is something that you may never reach. It may not be a point where the derivative is 0. It may be a point where it's an extreme, you know. But so this technique of finding maximum and minimums, what I'd like to leave you with on this is that it is once again an example of a dynamic view of the world, where you're looking, instead of looking at the absolute quantities that you're interested in, like the areas, we look instead at the change and how the things are changing. And so that's a different perspective, and I find it sort of philosophically satisfying to see that different point of view. Well, I'd like to look at some other examples of finding maxima and minima that are of a totally different character. And so for this, I'd like to begin with an example of a problem that was posed in 1696. Now remember that calculus was just invented at that time. Calculus had been invented by Newton and Leibniz in 1660s and 70s, and so it was a relatively new point of view, and one of the and it was being mined for all of its implications. And one of the things that was happening was that people would pose questions, challenge questions they called them, and publicize these questions and have people work on them. And one of the challenge questions that was posed by a mathematician by the name of Johann Bernoulli was called the brachistochrone problem. Brachistochrone comes from the Greek words meaning brachy, meaning shortest, and chrone, meaning time. And here was the problem that Bernoulli posed. He said, suppose you have 2 points in space. 2 points. They're not on top of each other, but they're just 2 points. And he said, suppose that you want to roll a ball from the top point down to the bottom point. The question was, what shape path should you make? Sort of a groove, think of it as a path on which a ball will roll. What path should you make so that the ball will end up at the bottom in the quickest possible time? Well, this was an interesting challenge problem. One thing that it makes it interesting is that there's an obvious answer to the question of what is the shortest path between the top point and the bottom point. It's the straight line. And you might think that that's the fastest path to make the ball roll is just on that straight line, because it doesn't have to go as far as any other path. So that's the first guess, is just this straight line. Well, it turns out, as we will see later, that is not actually the path of fastest descent. But this problem was circulated to people, to mathematicians around Europe at that time, and Bernoulli was famous. Johann Bernoulli was famous for having controversies with his brother Jacob Bernoulli. In fact, there were 8 Bernoullis who were very famous mathematicians and physicists who lived during that century, and they would fight with one another. And so one of the things that Johann wanted to do is to pose a problem that his brother couldn't get. You see, that was part of the challenge. But in fact, his brother did get it. There were 5 mathematicians, in fact, in Europe who were able to solve this Brachistochrone problem. And one of them was Sir Isaac Newton. Newton received this problem in the mail, and at the time he was the master of the mint. It was 1697 when he received this problem, and he found these challenge problems annoying. And part of the reason that Bernoulli posed the problems was to try to show that Newton and his method wasn't really as good as Leibniz and Leibniz's strategy for calculus. So he would pose these problems, and this was one of them. Well, so Newton had been working at the mint and came home from the mint and said, and he'd been living with his niece, Catherine Conduit, and his niece wrote this about what happened. When the problem in 1697 was sent by Bernoulli, Sir I.N., Isaac Newton, was in the midst of the hurry of the great recoinage and did not come home till 4 from the tower, very much tired. Worked very hard, worked all the way till 4 o'clock. But did not sleep till he had solved it, which was by 4 in the morning. So he had solved this problem in 12 hours. He was able to solve this problem. And incidentally, the solution of this problem requires inventing a whole type of calculus called the calculus of variations. It's amazing. But I also have to say that in reading some history, I'm not an historian, but I read some history about calculus, and I have to tell you that the same story was told about another problem, so I'm not sure how accurate this was, and it was also told about Leibniz solving this problem. So I'm not 100% confident that this history is right. But what I wanted to do is to demonstrate the solution to this problem. It turns out that the correct path for the ball to follow is a path that is constructed in a way by a wheel. And so I'm going to need some assistance from the audience. So Virginia, would you come here, and we will demonstrate this path by actually drawing the path. And the path that I'm about to draw is called a cycloid because it comes from a circle. And this is a big circle, as you see here. And the path is made by simply rolling the wheel along the ground and seeing what path it makes on the surface. So here we go. Roll, 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 roll. And that, that's pretty neat. That is the, there. Now, you turn it upside down, and this is the path of fastest descent. So this is the path along which, if you drop a ball, it will end up at the bottom at the quickest possible time. Now, you're wondering, oh, is that really true? Why is it? Okay. So what we need to do is actually demonstrate that this is true. And so we've actually made some roller coasters for balls over here that will demonstrate at least that this path, which is the same as the path we just generated there, that this path, the cycloid, is going to be the path of quickest descent. So to demonstrate this, we'll actually take two balls and roll them down. Now, of course, it won't demonstrate that this is the fastest necessarily, because there may be other paths. And indeed, the thing about this problem is that it's not just one quantity that's varying, but there are many different shapes that you could imagine to go from one point to the other. Any curve could go, even a ridiculous one that goes up and down, wouldn't be the fastest, but you'd have to consider that. So the reason that this problem is much harder than the camels is because of the possibilities are so much more varied. But at least let's see that this straight line path from a point that is at this height to this point down here, let's see that at least this cycloid path is faster than the straight line path. So I'm going to put we have black and blue balls, and we're going to put the blue on the fast curved path and the black one on the straight path, and I'm going to let them go, and we'll see which one arrives at the bottom soonest. And I hope you can see this. Okay, ready? 1, 2, 3. Did it work? Let's try it again. Okay, so which one was the blue one on the curved path, on the cycloid, the black one on the straight one? Ready? We'll try it one more time. Ready? Let's do it one more time just to make sure. Okay, so the blue one. By the way, I did want to say one other thing about this cycloid curve, which is really amazing, and that is that it turns out that this is not only the brachistochrone, but it's also called an isochrone, meaning that it doesn't matter where I start the ball on this curved path, it will arrive at the bottom at exactly the same amount of time. Okay, let's see here. So let's just to, well, I'll see if I can. I'll just try it one more time. Oh. Okay. Well, anyway, enough for the rolling balls now. I wanted to tell you one other problem of a maximization problem that comes from ancient times, and that is so-called Dido's problem. So Dido was a queen of Carthage, and she was given as much area for Carthage as could be enclosed by the hide of an ox. And well, it doesn't sound very like a lot of stuff, but what she did, and this comes up in Virgil's Aeneid, by the way, and what she did is she cut the ox hide into very thin strips, and then she had after doing that, she had, of course, one loop of string. And the question is, the mathematical question of Dido's problem is, what shape can you put a given length of string in to enclose the biggest area? And you might think of a square, or a hexagon, or you might think of all sorts of different shapes, maybe an oval, maybe an ellipse. But of course, the answer is, as you probably would guess, the answer is a perfect circle. And so this was a reference to from ancient times about a problem that was a very practical one. How can you enclose the biggest area with the hide of an ox? Well, this completes our series of discussions about the derivative. And in the next 2 lectures, we're going to talk again about ancient times, and we're going to be talking about ancient precursors to the integral. And these are wonderful because they give geometric methods for finding out things like the formulas for the area of a circle and the volume of a sphere that are very geometric, and they use the ideas that we have seen before and will see again in the integral. So I look forward to them. Bye for now.